Hey guys, I'm in our classroom. Thought I would post a quick lecture of our material that's coming up. Obviously this week we have our test on chapters 5 and 6, but you do need to start looking at chapter 7 pretty soon. Some of the assignments and homeworks and everything are going to get into that material soon. So this material will be posted in D12, so keep an eye on it. Anyway, chapter 7 probably is the most important chapter in the book for you guys to read through and make sure you know most of the material. But again, I want to help you out by telling you the things that I think are important as we flip through. Okay? So in the PowerPoint, the very beginning just talks about the history of the periodic table, how it was developed, all that kind of stuff. For the most part, I think you should know that Dmitri Mendeleev is credited with developing the periodic table, but there is a more complicated history to it. Several people that were all kind of racing to develop the first periodic table. Again, don't overly worry about it, but you do want to know some information about how the periodic table is arranged. The primary characteristic is the atomic number, the number of protons for each element. That's the order that the elements are listed. Some people think it's by weight, but it's not. There are a couple of places where a heavier element actually comes before a lighter element. So you have to go by atomic number, but there are important details in each group has similar chemical properties. Each period there tends to be a steady change in the properties as you go from metals to nonmetals, and that is what this chapter is all about. So you need to read that stuff pretty closely. Again, don't worry too much about the history though. I'm going to keep going, organized by the atomic number. So periodicity is the pattern of a property of elements based on atomic number. Again, as you go down the table or across the table, there's a trend in the properties of the elements that you can see similarities between certain elements, and then as you move across, you see changes in the properties as you go. The specific properties that we're going to focus on in this PowerPoint are, we're going to talk about the size of atoms and ions, which is referred to as atomic radius. We're going to talk about how much energy it takes to remove electrons and how you can compare different elements in that way. Electron affinity is how much energy it takes to add an electron to an atom. And then some other just general property trends that we see. But in order to talk about all that stuff, there's a fundamental property that we need to learn about first called effective nuclear charge. It is very important to, as a explanation, this is important explaining why these other trends follow the patterns that they do. So, our first one, effective nuclear charge, we need to talk about what that is. In my mind, in the simplest terms, every electron that's orbiting an atom, so here's a valence electron, it feels a certain amount of pull from the nucleus, kind of like a satellite orbiting the Earth feels a gravitational pull toward the center of the Earth. Here, electrons are attracted to the nucleus by the attraction of opposite charges. The stronger that pull is, the greater the effective nuclear charge. Okay? So, what determines how strong the effective nuclear charge is? Well, there's three main factors. First of all, the further away from the nucleus an atom is, the weaker the pull. Also, electrons repel each other. So if I have an electron in the fourth shell, the electrons in the first, second, and third shell are between those outer electrons and the nucleus, and the third shell electrons are going to be repelling the fourth shell electrons and kind of pushing them away. So that kind of counteracts a little bit of the effective nuclear charge. So the first two, these are two things that more distance from the nucleus and more core electrons are both going to cause the effective nuclear charge to get weaker as we go to larger shells. But then at the same time, when you go to bigger atoms, you're also increasing the nuclear charge, meaning the number of protons in the nucleus. A big atom has more protons. With a stronger positive charge in the nucleus, that's going to pull the electrons harder. Okay? But as we go from smaller atoms to bigger atoms, the top two factors tend to dominate over the third one. Especially if you look at each row of the periodic table, the elements in the first row and the second row are smaller, so the electrons are pretty close to the nucleus. Every time you drop down a row, the distance from the electron to the nucleus gets significantly bigger. So these two end up being the main factor. The third one, the charge, it's a factor as we move across one row. If I compare, like in the second row of the periodic table, if I look at carbon, oxygen, nitrogen, and fluorine, which are all right beside each other, all of those are second shell elements. And so the first two factors don't really change between those elements. They're all in the second row, so they're all about the same distance from the nucleus in the second shell. And they all have the same core electrons between the nucleus and the second shell, the only core electrons to be the first shell. And all the elements that I named have the same core electrons, so those two factors won't be a difference between them. That's when we look at the third factor, which is how many protons are in the nucleus. Okay? Now, in the book, it does talk about you can do a calculation of the effective nuclear charge. Z effective refers to the effective nuclear charge. Z is the atomic number. S is a screening constant, which is related to the number of core electrons. I'll be honest, I will not make you use that equation. It might come up in Mastering Chemistry once or twice, but it won't be on the quizzes or tests. Okay? So we're going to move on from that. I will say you should know, though, that at the bottom here, the property itself, effective nuclear charge, it increases as you move from left to right across the periodic table. So I would say oxygen will have a higher effective nuclear charge than nitrogen, and nitrogen will have a higher effective nuclear charge than carbon. Okay? Look at the periodic table for those three elements to confirm what I'm saying. The effective nuclear charge increases from left to right. If I go down, though, the effective nuclear charge gets weaker because, again, you're adding shells, you're moving further away, and you're increasing the amount of shielding between the outer electrons and the nucleus. Here's kind of a graph of all that. As I move across the periodic table, I can see the effective nuclear charge is increasing, but then as I go from group 2 to group 3 to group 4 and so on, they get weaker. So that brings us into our next trend. We're going to talk about atomic radius. Now, in order to talk about atomic radius correctly, we will have to make references to effective nuclear charge. Okay? Now, on the first learning check assignment, I believe that I asked you to I gave you a set of elements and said rank these from like smallest to largest according to atomic radius. I've already seen a couple of people that have submitted answers, and it said rank these by radius and then explain. Some people just said, well, the explanation is atomic radius increases as you move to the left and down. And so they ranked them based on that. That will get no credit. Okay? If you don't explain in terms of electrons and energy levels and effective nuclear charge why the atoms increase in size as you move to the left or down the periodic table, if you don't explain why, you don't get credit. Just stating that you memorize the trend is not an explanation for why the radius increases. So that's something I'm really picky about. Watch out for that on the learning check assignment, watch out for it on your quizzes, and watch out for it on the test. You have to give an actual in-depth answer to explain those trends. Okay? So first, we talk about the radius of an atom. How is that calculated? Because remember, an electron cloud out here, there's a nucleus in the center, there's a cloud out around it. As the cloud gets lighter, that means the likelihood of finding an electron is decreasing. So where would you cut off the cloud? And the answer is there's not really a good place. So what we do instead to define the radius, if we have a diatomic molecule, like let's just say this is Cl2, chlorine, two chlorine atoms bonded. If I look at the distance between one chlorine atom and the other chlorine atom from the center to center, the distance between them would be the radius of one atom plus the radius of the other atom. So the radius is defined to be half the distance between two atoms that are bonded to each other. Okay, so that's important. The trend that we're going to learn, so that's called the covalent radius, is what it's talking about here. That's half the distance between the two atoms. So the trend that we're going to learn, again, this is what we memorize, is that the atomic radius is going to be the smallest in the upper right corner of the periodic table. It's going to increase as we go to the left and down. Okay? We can memorize that part, but we also need to be able to explain why. Why do the atoms get bigger toward the bottom left corner? Well, I need to address two things. Why does it increase going left, and why does it increase going down? I'm going to address the second one first. It increases as we go down because every time we learned with electronic configurations, every time you drop down a row, we're always opening up a new shell, a new energy level for the electrons to go into. So hydrogen only has an electron in the first shell, in the 1s orbital. Lithium actually has, we just put an electron into the second shell. So the second shell is further out from the nucleus than the first shell. That explains why the atom gets bigger. If I drop down to sodium, now I've opened up the third shell. The third shell can be bigger than the first and second shell. So increasing on the way down is because we're dealing with larger shells. Okay? What about the decrease? Increasing as I go down is what I said, I think. It increases as I go to the left because across a row, if I were to compare lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, all those elements are in the second row. The electrons are in the second shell, but as I move across, I'm putting more protons in the nucleus. With more protons in the nucleus, there's going to be a stronger pull, which we called that earlier the effective nuclear charge. There's going to be a stronger effective nuclear charge pull on the electrons. If we pull them in tighter, that makes the atom get smaller. So as I move to the right, the atoms get smaller. Okay? Based on those two patterns, that explains why we see the pattern that's on the screen. Now, that trend only holds true for neutral atoms. Here's kind of a graph showing relative sizes of atoms, and what we can see, helium is the smallest atom on the periodic table, and down at the bottom, they don't show francium at the bottom because it doesn't really exist much on Earth, but rubidium is the largest of the commonly occurring atoms that we see. Now, if we look at ions, ions are going to be a little bit different from atoms in that, let's just say I take a fluorine atom, which I don't know if you can see it on the screen, but fluorine atom, the radius is 0.57, probably angstroms, but it could be picometers, but it's a 0.57 of some unit. If I add an electron to a fluorine atom, that turns it into the fluoride ion. I haven't changed the nucleus at all. But when you add another electron, the electrons in the outer cloud, they don't like each other. So when I add one more electron, it's going to make the electrons repel each other and spread out. It makes the electron cloud get bigger. So anytime I add an electron to an atom, which means making a negative ion, the atom's radius is going to increase. On the other side, with my metals, when they form ions, they tend to lose electrons. Well, for sodium, its normal radius for a neutral sodium atom is 1.66. If I take an electron away, its radius decreases to 1.16. Now, why would that be? Well, again, if you take electrons away, the cloud can shrink a little. But also with sodium, even more important than that, the outer electron, if I wrote the configuration of sodium, it would be 1s2, 2s2, 2p6, 3s1. If I take one electron away, that's the one that's in the third shell. If I get rid of it, that means my outermost electron drops to the second shell because I'm getting rid of the third shell. That's going to make the atom get significantly smaller when I go from a neutral sodium atom to a positive one. Sometimes with iron can exist as a neutral atom. It can be +2 or it can be +3. If I compare the sizes, the more positive the atom becomes, the smaller it gets. The more negative an atom becomes, the bigger it gets. That's the trend you need to know. Again, you should be able to explain it as I did. And then The only other topic on this that I want to cover is isoelectronic series. Iso means the same, so it's a series of atoms that have the same number of electrons. If I look at these ions listed right here, are all isoelectronic with neon. Neon has 10 electrons. If fluorine gains 1 electron, it normally would have 9, it gains 1 electron, that makes it 10, just like neon. Oxygen has 8, it wants to gain 2 to be like neon. So for all these ions, these are the charges they want to have to be like a noble gas. Okay? I could determine a isoelectronic series for any of the noble gases up there, but this is one example of a set. Amongst these, if they all have the same number of electrons, then that's not going to be the key for the comparison, because they're all going to be 1s2, 2s2, 2p6. All of those have the same configuration. But what is different is the number of protons. Oxygen only has 8 protons in its nucleus. Fluorine has 9. So if I were to compare those, they both have 10 electrons in the cloud, second shell. But if one atom has 8 protons, the other atom has 9 protons, the one with more protons is going to pull the electrons in tighter. So a fluoride ion will be smaller than an oxide ion. If I compare to the actual sizes, I see that that's true. Actually, the oxide ion is 1.26, the fluoride ion is 1.19. So the fluoride ion is a little bit smaller because it has a stronger nucleus. I'm going to cut off here, and I'll start another video in a minute with the rest of the PowerPoint.